Today, we're going to use fluid simulations to simulate birds. Where does that idea come from? Well, it all starts with something called Boids. Now, this is something you might have heard about before. Boids are just an example of a flocking simulation. This is where birds move together as a group. You might have seen this many times on YouTube before. Now, there are three simple rules for Boids. First is separation. Every bird tries to maintain a minimum distance from its neighbors. Secondly, there's alignment. Every bird is trying to move roughly in the same direction as its neighbors. And thirdly, we have cohesion. Groups that are close together want to stick together as well. And when you put all these rules together, you get some interesting behaviors. Now, obviously, if you have just a few Boids, like we have 8 here, you're not going to get these interesting behaviors. So you have to really scale up the number. You can have tens of them, you can have hundreds of them, and really, this is the point where interesting behaviors start to emerge. As you can see here, we're actually beginning to see flocks that are merging, that are changing, diverging from each other. And I really like increasing the number of these agent simulations. So I asked myself the question, what is the most number of Boids that I can simulate and see what cool and interesting behaviors they have? Here we have about 1200 of them. Again, as you can see, you get these really interesting murmurations, much like you do in real life, in nature. But how much can we scale these up? Really, there's some limit to the computation. Here we have 4,000 of them. Can we keep going? What if we have 50,000? As you can already see, the simulation is not as crisp as it was before. It's beginning to move a little bit more slowly with these many agents. And if we try to even have a few 100,000, well, forget about it. The simulation is no longer real time. And I want as many Boids as possible. So what do? I want this to run in real time. I want to be able to see these cool behaviors, but we cannot do an agent simulation to actually see giant numbers of Boids. So we use an insight, which is we find a parallel between Boids and fluid simulations. What am I talking about? Well, here is a classic equation used to simulate fluid dynamics. And what we can realize is each of the terms in this equation maps to one of the behaviors and the rules that Boids follow. So first, the pressure term can be thought of as both the separation that we talked about, as well as the cohesion that we talk about. So pressure is really about the interactions and the distances in between the Boids. Secondly, the viscosity term in this fluid equation can be thought of as alignment. The fluid that is close together wants to move together. And similarly, the Boids that are close together want to stay aligned with each other. And then the self-propulsion that we think of in a fluid that is, let's say, heated and is able to actually move or convect can be captured by the constant speed at which the Boids move. And finally, the motion of the whole group can be thought of as advection, which is the movement of particles in a fluid caused by the fluid itself moving. And one overall rule that we keep in mind is we want the head count or the total number of Boids to stay the same. And this is the continuity rule for the equation side of fluid simulation. So we don't want to lose any mass. Everything stays consistent. Now, if we put all of these rules together, what we get is the full fluid simulation simulating the Boids behavior. So let's take a look at that here. Now, this is a few thousand Boids. They're moving quite fast, so let me actually pull up my parameters and slow down their speed a little bit. As you can see, we have about 4,000 Boids here right now. And this is cool. This is how many we were able to get with the agent simulation as well. But what if we really crank the number up? Let's go to 16,000. And I can use my handy shortcut here to reset the Boids so we can see a behavior starting with a random group of them. And so this is already really cool. I love these swirls that are happening in there. You see these giant groups forming, these flocks forming. You can also see that over time, the alignment of the Boids starts to become more coherent. They're sort of heading in the same direction. But let's go even further. From 16,000, let's go to 66,000. And here again, you can see we are seeing these really interesting behaviors where multiple groups are almost cutting through each other, running across the screen. Now everything is wrapping around, so that's why the Boids that are going above are appearing from below. Let's keep going. Let's add more Boids. Now we can get to even 262,000 here. And I'm gonna just reduce the size of the Boids a little bit so that we can see really how many of them there are there. Well, this is a really cool behavior here. We can see there are two distinct flocks, one moving from bottom to top and one moving from the left to the right. And they're kind of cutting through each other, but the one going from left to right ultimately gets absorbed, and we just get this giant group going from bottom to top. Let's keep going further. Let's go to 1 million Boids. And again, we're just gonna randomize their starting positions so that we can see more interesting behaviors. And here very quickly, you can see that this purple flock that has emerged is slowly over time absorbing these other flocks that exist. But this yellow and green flock on the right is still taking some time to get absorbed. Oh, actually the purple flock, it looks like is getting absorbed by the greenish yellowish one. Oh, I just love all these cool behaviors, and I love being able to see them in real time. You can render these types of Boid simulations even using agents, millions of agents, but then you have to do it offline, and that's just no fun. Waiting 5 or 10 minutes for something like this to render, as opposed to just being able to see it in real time. And so let's keep going further. We can do even more. So let's go to 4 million. And here we can see, we can reduce the size of the Boids even a little bit more so we can see them better. Maybe even increase the speed of them so you can see the interactions happening faster. And at this point, really starting to feel like both sort of a fluid simulation as well as a simulation of birds. These sweeping motions remind me of gigantic flocks of birds that I've seen in nature documentaries. I love this snaking formation that has happened across the screen now. So it is one flock that's heading all in the same direction, but within that, it has these really interesting tendrils almost coming out of it. But over time, it is diffusing. Let's keep going. We can actually, in this simulation that I made, go all the way up to 17 million Boids, which is way more, orders of magnitude more than what we can get with just a simple agent-based simulation. Let's randomize this again from the start. Oh, that's absolutely beautiful to look at, I feel like. You can see all these vortices almost, which both to me look like fluid simulations, obviously, because we're using fluid simulation equations, but then also what it would look like if we had 17 million Boids all moving in the same direction. And one interesting thing we can do also is we can add an obstacle in the middle and do that again. And now as they move, they have to move around this obstacle, and then that gives rise to these vortex shedding type of behaviors as well. So when a flock hits the middle obstacle, it has to go around it, and then you see this swirling behavior that you're seeing right now, which is really, really fun. Now, at the end of the day, this is a simulation. So there's some fun things we can really do by pushing the simulation to its limits. So what I'm going to do here is I'm going to bring us back actually to about 4 million Boids here, and we're going to have some fun. So here are some key parameters that we can play with for this simulation. So first of all, let's talk about cruising speed. So this is just how fast the Boids are moving. So if I move this really fast, you can see that the groups start moving really, really quickly. And that almost makes it look like a wind tunnel or something. They're moving really fast. You can see these fluid-like behaviors. And ultimately, the color coding shows you how many different flocks there are. So it reduces to one flock. We can randomize this again from the start. This obviously is way faster in speed versus what birds would be able to move in real life. So that's why these are no longer realistic or depicting what you would see in nature, but is quite interesting regardless to look at. All right, so let's move down that cruising speed again to something more realistic. And the next parameter here is randomness. So this is how much individual particle's direction is random versus being moved by all those rules that we talked about previously. So the more random that we go, the more you'll see that it's sort of not really flocking anymore, and more these little tendrils that are moving everywhere. And if we actually have high randomness and high cruising speed as well, then you start to get these really interesting behaviors that personally to me don't really look like anything in nature, but maybe if there's people who are physicists out there, they can tell me this looks like something that they've seen before. I'm gonna get rid of that obstacle actually. Yeah, this is fascinating. So I can almost see bird-like behavior in there actually. Ultimately, it comes back to a flock. Let's randomize that again. Yeah, it starts with these really interesting swirly patterns, and then eventually gets back to a Boyd-like behavior as well, which is quite interesting. So that's randomness. Let's tune that back down to maybe a middle type of value. And let's maybe move down cruising speed again. All right, personal space is just how much space each Boyd wants around itself. So the more you increase it, the more they want to disperse. And so the more you're gonna see the Boyds sort of staying apart from each other, and they're not gonna collapse into these thin waves that we were seeing before. And this is fascinating as well. I love these little eddies that start forming, almost like tornadoes or weather effects that you would see. And again, here you can see it ultimately collapses into one gigantic flock, which is really interesting as well. Right, that's personal space. And then friction is just how much slowdown and how much the speed sort of decreases over time. And so if we increase friction by a lot, fluid's going to slow down as well. And glow is just for aesthetics, sort of make it look more like a sky in the background. I'm going to turn these down again. Now, something really interesting that happens is if I collapse personal space to absolute 1, I increase cruising speed quite a lot. And we're going to go back to actually 17 million Boyds here. I'm going to reset this. You get these really interesting, almost plasma-like, lightning-like effects. And as you can see, these fixed points start forming. You can see almost this black hole-like thing in the middle. If I start in different random positions, you can see how that works. Actually, let me decrease the cruising speed here. Increase the glow a little bit so you can actually see what's happening. So there you see these really fascinating behaviors in the liquid itself. Let's maybe bump us down to something like 1 million Boyds here so we can see this behavior even better. We get these fixed boundaries between these black hole type behaviors, these fixed nodes. And there's some other viewing properties that I've also added which show you, like, you know, in different spaces what everything looks like. So we're just gonna go back. This sort of shows you the phase, for example. And yeah, it's just really fun to play with. Increase the size of the Boyds again, decrease cruising speed a little bit, increase the randomness a little bit, give them more personal space again, and boom, all those Boyds that had just collapsed show up again, and you go back to that flocking behavior again. So this is really fun to play with. Hope you had fun looking at these cool simulations that I've been doing, and hope you have a good rest of your day. Thank you so much for watching.